Hello, everyone, and thanks for joining this webinar. So today we're going to talk about the Hawk project, which is funded by the SCAI, conducted by ourselves in Composites Testing Laboratory with University of Galway, Zero Nexus, and help from Airborne Wind Europe and TU Delft. So we have four speakers today. We're going to have Kristian Petrick up first from Airborne Wind Europe, and then myself from Composites Testing Laboratory. Then we'll have Vahid from University of Galway, and then we'll have Edward from Zero Nexus. So I'll hand over to Kristian first because we have a lot of, four speakers, and try and get through everything within the hour. So I won't hang around, and yeah, I'll let you take off there, Kristian, when you're ready.
Okay, thanks you very much, Cormac, for inviting me to this webinar, and thanks also to everybody who's working on this project. My name is Kristian Petrick. I work for Airborne Wind Europe. That's the association of the airborne wind energy sector. And I will give a short introduction about what is airborne wind energy, because not everybody may know that, and then also show a little bit the approach that we are taking with regards to standardization. And later you will hear much more about that. Unfortunately, I will have to leave more or less right after my presentation because I have overlapping meetings. But if you have any questions, then maybe we can do that just right after my presentation, but also the others would be able to answer them, I guess. So you should all see my screen. Just a brief introduction on Airborne Wind Europe. We have a little bit more than 20 members, and about half of them are technology developers of airborne wind energy systems. You see them more on the left side of this box. And we are members in various networks and other associations. We have our own Task 48 within the IEA Wind Technology Collaboration Program. And yeah, we collaborate with research centers and also SCAI on various topics. And for us, Ireland is an important country as well, because we have, as I will show, one of the key test sites in Ireland. So what is our technology looking about? We have both soft wing systems and fixed wing systems. That's basically what will, or these different concepts will probably also prevail in the future, because for different applications, you better use one or the other type of system. How it's working, you may already have seen it on our website or have heard about it. So the main concept is to have a ground generation system. That means that the kite is flying out in figures of 8, as you can see here. And by pulling out the tether from a drum, the drum turns, you have a generator next to it, and that produces the energy. And as you have just seen, once the tether is pulled out completely, the kite has to drawn back in, which requires a little bit of energy, but a lot less, and it goes much faster than during the power production or generation cycle. There are other systems as well, like generation in the air, but most of the companies are going for this ground generation system. Why are we doing all that? One reason is that we can tap into the wind resources at high altitudes, up to 800 meters. What you can see here is the wind resources in Europe at 100 meter, at a fixed hub height, so to speak, of conventional wind turbines. And all the reddish colors are basically onshore, and these are the really good potentials, actually. So offshore wind has a much higher potential than onshore, and that, as you can see, or there's higher wind speeds. Now, if you can go up to 500 meters, you see that large parts of Europe turn into red color, which means that the wind potential in these higher altitudes is much better, which means that the power output is also higher. So we are tapping into this so far untapped resource by flying in higher altitudes. And just for Ireland, zooming in, Ireland has in general already good wind resource, even at hub height or at 100 meters. But if you can go even higher, then you see that there's even much more potential. The other important reason why we do airborne wind energy is that we reduce the amount of material that go into the system. We basically emulate just the wing tips of a wind turbine, and the wing tips are the part of the turbine that actually produce most of the power. So we get rid of the tower, the blades, foundation, and a lot of material, and even rare earth materials, because we can put the generator on the ground, which means that we have a lower life cycle impact on from the life cycle analysis, and lower global warming potential, which is already very good for wind and solar, but we are even below that. So that's another reason why we think that's a very sustainable technology. I mentioned this test site in Ireland. That's in Bangor Airways in County Mayo. You see here the company Kite Power with their kite in one of the hangars. So you see that's a large kite, 100 square meters roughly, and they are becoming even bigger. I show just a short video of how this looks like, the beautiful site here. And you see the kite flying there in figures of 8. I hope it's very small here, but hopefully you can see it. Here you can see the kite coming down. But that's basically the what you see from the system. So it's not a whole lot, and that's one of the other reasons why we think we can be deployed in areas where either for visual impact or because the ground is not good enough or whatever, we can actually put up airborne wind energy systems and harness energy where it wouldn't be possible with normal wind turbines. And when you think, okay, you don't want to fly over roads and buildings, we have done now a GIS analysis on potential sites in Ireland, but also in Germany and Netherlands. And we are conducting the same study for Spain, and France is coming up as well. So you see here thousands of sites in Ireland alone in the base case scenario, and several gigawatts can be deployed there. The report will come out soon, but you see there's quite some potential for these systems. Ireland is also, as I mentioned, really important because we have collaborated in a number of projects, or are collaborating, for example, this demo project, or also the Hawk project that is presented here today. We have partners in Ireland, and we as we see that there's also a lot of potential and collaboration also with the aviation authorities. This is really an important country for us to further develop the systems, but also then to deploy them. So coming now to the standardization part, I mentioned already the aviation authorities, because this is the specific thing here with our technology, that we are at the crossroads, so to speak, between wind energy sector and aviation or aerospace sector. On the one hand side, on the left, you see in the wind industry, you have certain certification bodies, standards organizations, and the focus is really on power generation. Everything is about wind turbines at the moment, which is good. So we are complementary. We have nothing against wind turbines, but all the standards are really focusing on these 3 blade horizontal axis wind turbines. But we are different in that regard, so we need adjustments with regards to these standards, because we just look differently, although we do also the same, or our main product, so to speak, is electricity. But then on the right-hand side, you see that as we are flying, we also have to deal with the aviation sector and the standards that are there for unmanned aerial systems. We have other competent authorities. We have a different focus because if something is flying, it can fall down. So the risk analysis and all these kind of things are different. The regulation is different. Partially it's European, partially it's on the member state level. So we have to see, or we have to develop the right way on how to get into this. And the approach that we are taking is basically, first and foremost, our reason is power generation. So we are not flying because we think flying is so great, but because we want to produce power. So that's why we focus in the first steps on the IEC 61400 series, which is the main wind standard for the industry. And what we have now submitted is two new work item proposals. One is saying we want to have work on a new overview standard for airborne wind energy. So having a IEC 61400-80, because we are flying in figures of 8 or circles, 80 series, which provides basically an overview of the system components and is kind of mirroring what is there in the -2 series on small wind turbines, which is much more lenient than the large -1 series for big wind turbines. So we don't need everything at once, but we want to give an overview of the different system components and what is important for those. And the other one that we submitted is to say, okay, we can also already use a lot of the existing IC series. For example, the one on performance measurement, the -12 series, and we would just adjust that for airborne wind energy. So there would be a sub-series -80 again, which would define on how power performance is being measured for airborne wind energy systems, because as you can imagine, it depends on the altitude where the kite is flying. There are certain things that we have to do differently than a wind turbine, also because we are moving, and yeah, so there are a few parts that need to be adjusted, not a whole lot, but some of them. And last year, one of our member companies, Sky Sales, they actually got the first externally validated power curve, which was applying already these ideas. So based on the IEC 61400. So there is some experience now, and we will use that to develop then the standard over the next months. The approach of basically using IEC as the standard or as the basis, and then only plug in the aviation standards where required, was also confirmed or shown, recommended by a study that was just coming out of one of our projects, the Mega-OR project, which was done by Aura Catapult from the UK. And also, and you will hear this a little bit later at the end of today in the presentation from Edward from the Hawk project, where Edward looked much deeper into comparison of aviation and wind standards. So I don't want to already preempt what he will say, but you will see these graphs probably in his presentation. So yeah, that was my part, and with that, I would hand back.
That's great, Kristian. Thanks very much. That was excellent. Okay, so I'll move on to my own presentation now. Okay, so hopefully that's showing up okay. So I'm going to present on novel composite material database for fixed wing airborne wind energy kites. That's a bit of a mouthful. So basically we're looking at the fixed wing version, which would use more composites compared to the soft wing, the more kite shaped ones. So just a brief background, composites testing laboratory. So we test structural composites, mostly carbon fiber, glass fiber, that would be used in the aerospace industry, space industry, and renewable energy. A lot of what we do is research and development in these industries. We also do some testing for medical technology and sports industries as well. We do static testing, fatigue testing, environmental testing, physical, thermal, and microsection testing, and material receipt and relife. So just a scope of kind of what we do. So as part of this project, the main goals were to address the use of composite materials in the aerostructures. And this, I'll focus on the first work package, which was material and process characterization. So the first step of this was to review existing material databases. So there already are databases out there of composite materials that are used in industry, the aerospace and the wind industry. So first step was to review these, and then we sat down and we had interviews with all the developers of these systems, just to get an idea of what they were looking at and what kind of materials they were thinking of using. And then we select candidate materials, we create a test program and conduct all the testing on those materials. And then the last step was to create an open source database. So to publish all this test data and make it freely available to airborne wind developers and anyone else in the composites industry that might make use of the data. So that's the scope of what we were looking at. So reviewing the material databases first. So in aerospace, the main database is this NCAMP database. There's also this SHM and CMH databases, this Composite Materials Handbook. And in the wind industry, there's this SNL MSU database and Optidat databases. So basically, these are well-known, well-researched materials that are used in aerospace and wind energy, and all the material data is available on those databases. So we went in, we had a look at all those materials, and we said we would pick novel materials that aren't included in these databases because it didn't really make sense to double up on what was already covered. So that was kind of what we decided with that. Now with our interviews, so these are the four companies that we interviewed: Twin Tech in Switzerland, Kite Mill in Norway, Mozero in the Netherlands, and Windlift in the USA. So they're the guys that we spoke to. Yeah, so when we were talking to them, we were trying to get an idea for what kind of scales they were looking at in terms of production and where they were at the moment. So kind of volume targets, their cost targets, what kind of maintainability, end of life, and certification, what they kind of had in mind or what they were kind of planning towards, I suppose. And then in terms of the parts themselves, what kind of shapes, what kind of structural layouts, would they be looking at transport and assembly? If the parts were going to be made in parts and assembled together, then you have to take other considerations. And then we have design standards, environmental and durability of the parts as well. So when we were looking at the parts, you could see it's these complex wing structures. So you have your skins, you have spars, you have stringers, and you have ribs. So it's all these complex shapes that all need to be assembled and bonded together. For materials, so you're looking at high performance composites. There's some flexibility in material costs. So there's thinking there that if you spend more on and you get a higher performing material, then you could get better energy returns from the system. So if you spend a little bit more on your capital cost for the material, you recoup that in higher energy output for your system. So there is that flexibility there. And they were thinking towards sustainability, recyclability of materials. So yeah, primary structures would require carbon fiber to meet the load requirements, and secondary structures would likely be glass, but also so there's potential there for some alternative fibers. And then the wings, yeah, complex shapes, and then over the next 5 to 10 years, some of the companies are looking between tens to hundreds of systems per year. So selecting materials. So we kind of looked at this rethink method. This was from Adam Smith in CKN Knowledge Network. So he proposed this way of looking at the composite materials. So to look at basically sustainability and more environmental impact as a whole of the product cycle. So we see here the image on the left is your wind turbines, other massive amount of material, and a lot of it goes to landfill. So we're trying to avoid that as much as possible in developing this new database for materials. So when it comes to the process factors, you look at material waste, you look at your energy consumption and the emissions and pollutions produced by the actual manufacturing processes themselves. And then the other side of it, you can look at the products. So you can look at the service life. Are there things you can do to extend the service life? make sure the parts are repairable, and is there recyclability at the end of life for that material. So in order to kind of compare the materials we selected, we picked a baseline material which is available in the NCAMP database. So this was a composite material, a carbon fiber composite from Solvay, and we took those processes and the factors in that composite and we compared them to the ones that we selected. So there's a lot of information on this slide, but basically this is one of the materials we selected. It's from a company called Cadhain in Spain, and they call it a 3R epoxy. So it's reprocessable, repairable, and recyclable. So this is distinct from the current epoxies used at the minute, where you can't do any of those. So these materials, you heat them up, you basically remelt the material, and you can reshape it into either new part, or you can repair any damage that might have occurred with the part. So we selected this material and we made panels using this HPT fabric. And then we looked at, so the differences with this material. So we're looking at process focus factors. So there's less material used because of the reprocessability. There's higher energy consumption because there's higher pressures required with this particular resin when you're manufacturing with it. But the main factors is repairability and recyclability with this material. So in the long term, it should be a more sustainable material to use. And then the second one we looked at was a Zoltex. So it was a unidirectional carbon fiber. So this is a pultrusion material. So it's a constant, continuous process where it's like extrusion for polymers, but you have your carbon fibers in there. So you get really straight fibers. So that's the product. When you look at product focus, you get better service life due to that better fiber alignment, and less energy and material waste due to just the continuous production process. Another material we looked at was this powder epoxy, or CPET, developed by Air Composites. So this is a powder epoxy, less emissions from this material when you're processing it, and the products. So it facilitates, because they can be cured, parts can be co-cured with this powder epoxy, so you can reduce the need for bond lines in the parts, so that improves the service life of the parts. And then we looked at a flax fiber, and this less emissions and less embodied energy required in producing these parts, more sustainable. So the test program itself, so this is basically the test matrix, all the tests we conducted. These are the averages for each material. We looked at tensile strength, compressive strength, shear strength, and modulus for each of these as well, flexural and interlaminar. So these are the average of each batch of tests. So there's the table of the test results here. So for example, this one, 6 individual tests. We have our stress strain curves, and your average is here, so 790 in that case for that material. So to look at this material, so what we did then was we compared it with this baseline. So this M45 MTM45. So this is one of the materials from the NCAMP database, and this line here is the values of that material, and we tried to compare this Cadhain 3R resin with those baselines. So we see here 0 degree tensile strength is about 80%. The modulus is quite similar. Our 90 degree is better actually, and our 0 degree compression strength is probably the lowest. So that's down there at 64%. So we can see there's not quite as well performing, but it's an early stage research material. So these NCAMP materials have been well researched and developed over years and years. So they're going to be better performing materials. So it's not a bad starting point when you're looking at a new novel material. And this is the Zoltex. So this is the UD compared with a UD from the NCAMP database. We see our 100% baseline here for the baseline material. So our 0 degree tensile strength is a good bit lower, 67%. and are 90 degrees. So that's, you'd look to improve on that really. I suppose one of the main things you look at is your 0 degree compression strength. So that is higher. So we're seeing 114%. So that's a good sign, and that's what you'd be expecting with the pultruded process. Really good fiber alignment and good material properties. So I'll kind of breeze through the last couple of slides. So we did fatigue testing on this Sidotech 3R resin. We got our SN curve here. It was a good bit of scatter in these results, but in general trend was quite good. We then tested three specimens to 100,000 cycles at 70% of the load. And they didn't fail. So we ran those and we stopped at 100,000, and then we tested them afterwards to see what the knockdown factor is here. So that's our static strength of 764, and then a residual strength after fatigue of 722. So it's knockdown of about 5.5%. So that would give designers kind of an idea of the effect of the fatigue life on the material. And then we did the same for the Zoltec. We did fatigue, and we developed our SN curve here. We didn't have enough specimens to do any residual tests on that material, so we don't have that data. And then the last step was to create the database, open source database. So we're going to publish this online on this zenodo.org, which is open access. And that'll really give developers a leg up when it comes to selecting these new materials. And then just in general on the project, so we had 2 conference papers out of the project so far and 3 presentations at the Airborne Wind Energy Conference. The 2 conference papers were at the COER 2024. And then there was 1 white paper published by Ed on Zenodo as well, on Airborne Wind Energy Certification Roadmap. So Ed's going to present also on that piece of research as well later on. So that's it. Cormac. Thanks for listening. And I will hand over. So up next then is Vahid, and he's going to present on the FE modeling, some of the finite element modeling conducted. So yeah, I'll hand over to yourself, Vahid.
Hello everyone, I am Vahid, an assistant professor at Maynooth University and a member of Center for Ocean Energy Research. In my previous career at University of Galway, I worked on HOG project, and I am going to have a presentation on durability and assessment of the wing structure in an airborne wind energy system. After introduction, I will talk about finite element modeling, aerodynamic loads, static analysis, fatigue analysis, and future studies. HOG project is funded by SAI with collaborators from University of Galway, CTL, TU Delft, Ghent University, and Zero Nexus. Airborne wind energy systems consist of an aircraft and a ground system that are mechanically connected by ropes. There are 2 types of airborne wind energy systems, ground generation and fly generation. In ground generation, the generator is located on the ground, and in fly generation, the generator is located on the aircraft. In this project, we consider the ground generation. In the ground generation systems, there are different types of aircraft, including rigid, semi-rigid, and soft structures. In this project, the rigid structure, which is like a kite, is investigated. The investigated aircraft is shown in these figures presented by TU Delft. It consists of fuselages, main wing structures, tails, and control surface assemblies. We are going to analyze the main wing structure, which is under extreme aerodynamic loads. The wing structure includes ailerons to control the flight, and also shear webs, ribs, stringers, and spar caps to support the loads. We developed a finite element model in Abacus based on the 2-Delft model. In this model, main wing, ailerons, shear webs, and ribs has been modeled with the shell elements. Hinge mechanism and actuators was modeled with the truss element, and finally, beam element was employed for fuselages, tails, stringers, and spar caps. The boundary condition was considered to be fixed at the wing box, and we used the novel composite materials in the HOG project that Cormac explained in previous explanation for the components as shown in this table. Aerodynamic pressure loads were calculated using a CFD analysis in ANSYS Fulent conducted by Ghent University. We received the nodal pressure distribution from CFD analysis to apply on FEM. This was a challenging step because the element size and meshing in CFD were different from FEM. So we employed interpolation methods in Hypermesh to map the pressure data from CFD into FEM. We received aerodynamic pressure loads from Ghent University for an optimized trajectory of the aircraft, as shown in the right figure in the green curve. Then the aerodynamic forces and moments were calculated for a complete power cycle, as shown in these figures. And then 10 peak load cases were considered for investigation. For example, for load case 1, the aerodynamic pressure distribution on the upper and lower surfaces of the wing structure are shown in these figures. Also, in this study, the Psi-Hill failure criterion was employed for strength evaluation of the composite wing structure. This figure indicates distribution of Psi-Hill failure index on the upper and lower surface of the wing structure. The value greater than 1 indicate failure. This table shows the maximum value of Psi-Hill failure index for all peak load cases. All values are lower than 1, which means that wing structure had a sufficient strength in the presence of the applied aerodynamic loads. However, load case 4 has the highest value. So for this load case, we investigated the distribution of the maximum principal stress as shown in this figure, and identified the highest value of stress around 310 megapascal. This load case was selected for a detailed fatigue analysis. For fatigue analysis, various fatigue predictive models were investigated, and finally, a stress life SN model was selected. This figure shows the SN curve for the main wing structure material, CDTEC, as presented by Cormac and tested by CTL. According to the results, load case 4 was the most critical, with a maximum stress fluctuating between 310 megapascal and a value near 0. So the stress amplitude is calculated, and the lifetime is predicted by SN curve, which is extremely high, which means indefinite lifetime. For future studies, there are some suggestions. Optimization of the wing structure to reduce consumed materials and cost, considering a wider range of loading conditions for static and fatigue analysis, and finally, investigation on other fatigue predictive models. Thank you so much. After end of presentation, I will ask your question. I hand over to my colleague Edward.
I think I'm the last presentation before we get into the Q&A. And following up from Kristian's presentation earlier, I'll give a rundown of the last work package in the HOG project, where we wanted to get into a deeper understanding of the sort of landscape for certification of airborne wind energy systems, and how they differ from conventional wind energy systems, horizontal axis wind turbines, and what ultimately it means for the composite aerostructures that make up the wings, aircraft body, etc. So in this work package, we wanted to kind of take a wider view of what certification was initially, to identify what the overall development process could look like, identify what some of the major deliverables and developmental milestones look like for kind of the conventional aviation and wind turbine certification processes, and then look at sort of the risks and trade-offs for each of these industries' approaches, and how that would be applied to the airborne wind energy systems that have been described in the presentations up to now. So just to kind of get everybody on the same page, when we're talking about certification, we're really talking about this third-party attestation and review of products, processes, and systems, and the individuals' roles involved in delivering any particular product. And really, it all comes back to what are the processes for testing and verification that the original specified requirements for these systems have been met. The challenges for airborne wind energy systems are that they kind of fall in between conventional wind and aviation. So both certification regimes have relevant considerations for airborne wind energy systems. We still have an aircraft. It's operating typically as an autonomous drone, though at times it's maybe being radio controlled, but it's not got any pilot or people directly in the aircraft. It's operating in a contained area. Certain systems can't fly independently of the tether, so you have an airspace, a different sort of airspace regulation that's going to be relevant to airborne wind energy systems. And ultimately, for the early systems, when they're operating in restricted areas that the general public won't have access to, it means the risk to individual lives and safety is much less than with conventional aviation, though potentially more than with conventional wind turbine systems. So each of these industries have overall different requirements, different rules, different processes to follow when you're going about getting a product or an organization involved in the design and manufacturing of these systems certified. And each industry's supply chain adheres to those particular rules, and there doesn't tend to be a huge amount of overlap between them. So these are some of the challenges that we wanted to address when we were looking at the topic of certification. So building on a lot of good work that's been done by Airborne Wind Europe and other groups and the MEGA project, we looked at how airborne wind energy systems are scaling with size, airspeed, and power. So looking at the initial kind of pre-commercial systems that are out there right now, these looking just at the rigid wing system, since the focus of this project is on the composite structures. Pre-commercial systems are maybe up to 8-meter wingspans, tend to be roughly under 25 kg in the kite weight. Their airspeeds are up to 50 meters per second, and they're less than 50 kilowatts in power. As you scale up and look at these early commercial systems, so you're getting quite a bit bigger. You're up to 20-meter wingspan, 600 kg in mass, and up to 100 kilowatts in rated power. And looking at the final stage that a lot of developers are working towards with the fully commercial systems. Here, the max weight really jumps up, the mass of nearly 6,000 kg for the aircraft, and up to 2 megawatts for power output. Now these aren't hard limits, but conceptually this is what the industry is kind of trending towards. And what this really means is that there's different risk categories and classifications of risk for each of these groupings of systems. So when we're looking at the roadmap to certification, we started by mapping out the type certification and project certification processes for conventional wind turbine systems. I won't go through them all in detail, but just to give you a rough idea that in pre-certification, there's the early design stages or activities. Certification involves getting a type certificate for the particular type of turbine system, and that translates into, or is a component of getting the wind farm project certified. And after certification, there's a maintenance activity to just keep these certificates kind of fresh and relevant. Civil aviation is similar, but there's maybe one or two kind of key differences. In the certification process, there is a type certificate for the aircraft system, but there's also organizational approvals for the design organization and the production or manufacturing organization, which really focuses on what the design and manufacturing processes are and how they're managed and maintained. And then you have a bunch of different organizational approvals for general airworthiness and the maintenance and other, say, air operators, the actual kind of airports, airlines, those kinds of things. So you have a whole bunch of different certificates for different stakeholders that are involved in running a commercial aviation system. So what does this really mean for airborne wind energy systems? Looking at where we are on the pre-commercial to fully commercial roadmap, right now there's no certification required. We're in sort of a regulatory sandbox, no type certificate or project certificate, but from the aviation side to fly any of these systems, like the ones that are flying in Bangor Airs in County Mayo, you have to get a permit to fly by the National Aviation Authority. So that's the one sort of regulatory requirement that's out there right now. As we scale up towards commercial systems, there's kind of a lot of uncertainty. If you don't have any certification or only partial certification, and that uncertainty really is for the developer of the wind farm, whether they'll be allowed to fly their systems and whether you'll be able to get financing and insurance for the airborne wind energy farm that you're actually developing. But if you go too early to full certification, especially through the civil aviation approach, it becomes really uneconomic to actually be able to develop new and iterate on existing systems. So the roadmap really means kind of working towards, maybe using like Kristian described, going with this a certification approach through the IEA, using small wind turbine certification approach as a basis for it, looking at getting prototype type certificates and still maintaining permits to fly with the national aviation authorities. When we get up to fully commercial systems one day, ideally that will mean following the wind turbine certification process and having type certificates and project certificates specific to airborne wind energy systems, and kind of carving out its own space. And if we see a lot of developers and a lot of farms of airborne wind energy systems starting to scale, ideally that would be the approach that's taken. So I'll just touch on one last topic before wrapping up. this has been a lot of discussion of the high level process for certification, but we also wanted to look at what's actually required specifically for the composite structures. So looking at the type certification process, I won't go through the flowchart in detail, but in the initial stages, you have to set out what your design is, your design basis. So looking at the different standards that are involved in the wind industry on the left and the civil aviation industry on the right, we're able to map similar topics across each of the different standards. So we actually did that for a handful of topics. We looked at, say, composite material processing requirements, looked at what the wind standards, where there are kind of sections in each of the standards, what they say, map them onto the equivalent sections in the civil aviation standards. And in doing that mapping, we're able to identify any gaps in, say, the wind turbine approach that relate to airborne wind energy systems, like, say, blade root attachments for wind turbines. Obviously, an aircraft that's just tethered doesn't have a direct equivalent to a blade root attachment, but there should be some sections in the standards for AWES to address tether attachment topics to the aircraft. So we had a few different findings around differences in design standards, damage analysis approaches between the two certification regimes, how testing of components is managed in a verification program between wind and aviation standards, and how inspection is done over the lifetime of the system as it's being run. And all of that was documented into I actually don't have the reference for it here, but into a final report that's available on Zenodo, and references the overall roadmap and then the specific analysis of the different composites requirements. So I think I'll wrap up there.